Jnanam Paramam Dheyam. Knowledge is supreme.
Welcome to this lecture on advanced transition metal organometallic chemistry. We have been discussing a very important topic in the last two lectures, and this is about structure and bonding in transition metal cyclopentadienyl complexes. Now, cyclopentadienyl ligand had been an important ligand in the realm of organometallic chemistry, particularly for their stabilization of many types of transition metal complexes. Also, they are known for their reactivity and their properties. Now, as a measure to understand the exceptional or unique reactivity of these transition metal cyclopentadienyl complexes, one needs to look at its structure and bonding, and that is what we have been doing in the last two lectures. Now, the approach had been to build a molecular orbital diagram for these particular transition metal cyclopentadienyl ligand interaction, which are constructed from the various atomic orbitals of the ligand and the metal. Now, we had looked into interactions of metal orbitals with various ligand orbitals, which are mainly p type orbitals, and what we had seen that the cyclopentadienyl ligand has primarily 5 p orbitals, which forms various kind of fragment molecular orbitals through symmetry combinations of atomic orbitals. And what in the gist it turns out that these ligand orbitals can interact with the metal in 3 type of interactions. These can be this conventional sigma, pi and delta type interaction, which is sort of same as in other transition metal ligand interactions. But the unique thing about this particular interaction is, in this case the pi interaction is predominant, whereas the sigma interaction, which in almost all of the cases or according to conventional wisdom always had been the predominant, but in this particular case in transition metal cyclopentadienyl complexes, these sigma interactions are non-bonding, as well as the delta interactions are weakly bonding. So, which sort of makes that ligand to metal pi interaction in metal cyclopentadienyl complexes to be the predominant, and that sort of makes these complexes not only unique with respect to their metal ligand interactions, but also unique to various kind of properties they exhibit. Now, continuing further along this line, we are going to today look into the quantitative aspect of the molecular orbital generated as a result of interactions between the 2 cyclopentadienyl ligand and the metal orbital in a metallocene type of complexes. To start with staggered geometry, which is supposedly the most stable conformation for metallocene type complexes, and then one can start with a staggered geometry of the type Now, what we had said that this is the ligand. So, the ligand orbitals would be somewhere over here. The metal, let us say we assume iron being the metal. So, the ligand orbitals would be this is A1G and A2U. Then there are 2 sets of degenerate E type orbitals, which are E1G and E1U, and there are 2 high energy E2 type orbitals, E2G, E2U. Now, this A1 is supposedly involved in sigma type interactions, E2 supposedly involved in pi type interactions, E1G and E1U, and E2G and E2U involves in delta type interactions with the metal. Now, what are the orbitals of the metal? As for the metal orbitals, there will be 5 d orbitals, and they would be of A1G, E1G, E2G. So, 2 plus 2 plus 1 5, then one s orbital will be there. So, that A1G. So, this is a metal d orbital, this is metal s orbital, and then there will be a metal p orbital, there will be A2U and E1U. So, this is metal p orbital. Okay. Now, the interaction occurs as such that the A1G of the ligand interacts with A1G d type of the metal, okay, as well as with A1G S type of the metal, S type of the metal, resulting in A1G star, which is orbital somewhere over here, so this is A1G, A1G star, okay, as well as with this it gives A1G A1G star, and this is mainly d z square. Okay. So, one A1G interacts with two ligand A1G ligand orbital, giving 3 orbitals 1, 2, 3. One is A1G, A1G star, and A1G star. So, this primarily looks like non-bonding in nature. Okay. Then A2U remains pretty much non-bonding, does not find any interacting partner with any of the metal orbitals, in the sense that in the P has a A2U component, but this energy difference between A2U of the ligand and A2U of the metal is so high that the ligand A2U primarily remains non-bonding or does not interact. As a result, the same thing happens over A2U of the P, that also does not formally sort of react or does not have any component of interaction, but slightly antibonding. So, maybe having very weak interaction of A2U, and this one may have a very weak interaction from the P, and this is called A star 2U. Okay. So now all the ligand A1G, A2U have gotten engaged with A2U, A1G, A1G of the metal. The next comes this E1G interaction. E1G interacts with E1G of the ligand from the d orbitals, and that interaction is given as and it will also have a antibonding component which is somewhere here. So this is E1G star, and the metal involves are X, Z and Y, Z. Okay. So now E1U that remains over here, that interacts with E1UP of the metal, and so this gives E1U, this is E1G, and this is E1U. And one would then have E1U antibonding, which is way up in the top, E star 1U, which is over here. So that leaves us with the E2U and E2G orbitals. So E2G interacts with E2G of the D here to here, giving two sets of orbitals. This is E2G, and this is x square minus y square and xy. Similarly, there will be E2G star, which will be somewhere over here. This is E2G star, and that sort of engages that. So that leaves with E2U as the non-bonding orbital, E2U as the non-bonding orbital, which does not find any takers over here. Now this sort of gives the overall the molecular orbital diagram. Now for ferrocene, so the overall it's 18 valence electron compound. So that means that this is fully occupied 2, 4, 6, 8, 10, 12, 13, 14, 16, and this is 18. So 18 valence electrons are over here, and these sort of represents the various form of sigma pi delta interaction. Now remember, we had a discussion as to saying that why the sigma interaction is a sort of non-bonding, and that can be explained by two explanations. One was just a visual explanation, which I had discussed in an earlier class, saying that the ligand orbitals are on the periphery of the conar plane, whereas the metal orbitals are at the center of the cone. So the overlap of that being almost minimal, and that is the reason why this interaction does not happen. And the other explanation is this, that one can see that non-bonding nature even from the quantitative molecular orbital diagram that is shown over here, and which sort of says that if one looks at this bonding and antibonding orbital of A1 and A2, one sees that A2 is non-bonding, which is sort of not interacting, and A1 is sort of filled in the bonding and the antibonding as well, resulting in the overall bond order of 0. So that is a very important observation, which sort of says that even in the quantitative treatment of the Cp star molecular orbital diagram, that these sigma interaction is almost 0 or non-bonding in nature. So sigma is non-bonding, and sigma interactions over here are these. Delta interaction is weakly bonding. So this is a delta interaction. So this is delta weakly bonding. Why it is weakly bonding? Because this represents the delta interaction. So it is weakly bonding. Sigma is non-bonding because A1G and A1G star, they are both equally populated. So it does not, it sort of cuts off, and the predominant interaction thus are these pi interactions, which are sort of the major interactions. So let me just reiterate that sigma interactions are shown in red, pi interactions are shown in blue, and delta interactions are shown in green. And this provides very important treatment of this orbital interaction in ferrosinyl complexes. Now, I would also suggest the people taking this course to construct this molecular orbital from scratch, because while constructing, one can sort of get a real feel of how these orbitals are really interacting to give the molecular orbital of the ferrocene. And of course, there is this additional joy in being able to construct this molecular orbital of such complexity by following certain principles and then matching them up with the proper symmetry related orbitals of the ligands and metals, and then coming up with such a complex construction. Now, these orbital is sort of the DNA of ferrocene reactivity, because most of the reactivity that is observed or seen in not only ferrocene but other metallocene complexes in fact should be explained by the electronic structure as is constructed in this orbital, and hence this orbital becomes very important and relevant. Now, with this let me just go even further and said that even though this orbital diagram is shown for ferrocene complexes, but they are equally applicable to other metallocenes complexes where metal will change as a function instead of iron. And also the other important aspect is that this orbital diagram is also varied for various rotomers, so that the orbital energies would not really much change on going from eclipse to staggered conformations. They would vary slightly, the bond energy would not change. Now, proceeding further along the line, based on this diagram, then one has to also take a look at various other metallocenes, and one sort of says that by looking at the filling of molecular orbitals in this metallocene, one can sort of explain the paramagnetism work seen in other metallocene complexes and their electronic configuration and so on and so forth. So, we are going to discuss that subsequently in this lecture. So, these are ferrocene staggered conformations for D5, 5D, and also would be valid for D5H. So, now moving further, weakly bonding or non-bonding nature of bonding or non-bonding nature of E2 and A1 molecular orbitals called for existence of metallocenes with less than 18 valence electrons. For example, BCP manganese is 17 valence electrons. For example, BCP chromium having 16 valence electrons, BCP vanadium having 15 valence electron, BCP iron, which is ferrocene, which we have already seen has 18 valence electron. So, these treatment provide quantitative answer to magnetism observed for these other metallocenes which are paramagnetic in nature, and also explain hence their magnetic property, which is kind of very useful. Also, it is to be noted that these orbital diagrams which was shown for the ferrocene is different than the normal octahedral symmetry treatment which is given to transition metal complexes, in the sense that the orbital splittings in ferrocenyl systems are different from that the regular octahedral or tetrahedral environment that students are often used to. So, these this particular molecular orbital diagram explains the magnetic and the electronic properties of these complexes, and we are going to sort of take a look at it in bit more details. For example, we go back to this orbital, and let us take a look at this ferrocene electronic configuration, which can thus be written as A1G. For this, the electronic configuration is A1G, then A1U2, then E1G 4 and E2U 4, then E2G, E2G4 and ester 1G, 1G A2, ester 1G A2. So, this is the electronic configuration of ferrocene. Now, having said that, one can look at the electronic configuration of various transition metals. For example, Cp2 titanium plus, thus the electronic configuration would be A1 G2, A1 U2, E1 G4, E2 U4 and then E2G1. Now, titanium will have this is a 13 valence electron. So, 2 into 5 plus 4 minus 1 because so it is a 13 valence electron. So, this is 4, 8, 12 plus 1 13. Similarly, if one looks at Cp2 vanadium plus, then all these remains same and it becomes E2G3. Okay. If it is Cp2 chromium, then all of it remains same and then E2G E2G3 and A1 ester 1G 1. Okay. So, like that one can sort of explain the electronic configuration for much of the compound, and the detailed variation of this is shown in the table for various electronic configuration of various types of metallocene compounds and their species, the corresponding unpaired electrons, their spin Henle values, then calculated and expected to provide value for that. Now, with this I would like to conclude today's lecture, which involved a detailed quantitative treatment of transition metal ferrocinyl complexes. We have looked into the construction of the molecular orbital diagram using the interaction between the ligand orbital and the metal orbitals, and we have not only seen that how does it what is this the interaction about, but we also see how the orbital diagram can be translated to explain the magnetic property of various types of metallocenes and complexes, particularly their magnetic behavior and so on and so forth. So, with this I conclude today's lecture, and I am going to take up on the reactivity and the property of these types of complexes in the next lecture. Till then, goodbye and thank you.